Okay, let's talk about PaliGemma today. It is a 3 billion visual language model from Google, which can easily be transferred to many visual language tasks. And the main selling point of this paper is by using just 400 million parameter SIGLIP vision transformer and 2 billion Gemma language model, they're able to outperform much bigger 10x or even 100x larger vision language models. Okay, so this is the overall architecture of this model. Okay, the image goes through this SIGLIP image encoder and then it is linearly projected to the tokens, which are vision tokens. Similarly, the text goes through this sentence piece tokenizer and then we get the text tokens. Both of them are concatenated. So this linear projection layers actually map the vision tokens to map the dimension of these language tokens. And we will go through the code to see how it works. Then after concatenating these vision and language tokens, it goes through a standard Gemma 2 billion language model, which is decoder based model. And then the output is text. So the input is vision and text, and the output is just text. And they also showed that we can define number of tasks like that, including object detection and segmentation. So the input to the model is the image tokens or video tokens and the prefix text, input text, and the output is this suffix text. So this API of image plus text input and text output is very flexible, and that can cover many standard tasks. So image classification, captioning, visual question answering. So they even went beyond these standard tasks to pure image tasks like detection, instance segmentation, depth prediction, and so on. So for image encoder, they use publicly available checkpoint of SIGLIP. So SIGLIP is very similar to CLIP model, but they use the sigmoid loss line instead of softmax loss. And they showed that it performs much better and is more sample efficient also compared to CLIP. So if you want to use any image encoder, most likely SIGLIP vision encoder will work much better than clip vision encoder just out of the box. So, and the language model is the decoder only language model, which is Gemma 2 billion. And this Gemma, so this Gemma model is also published by Google. So if we go into the architecture of this Gemma model, so it's not very complicated. It's a transformer decoder based model. So the popular LLMs are decoder based models. So it is also that, and they added some detail of the design choice for this decoder based model, for using multi-query attention, rope embeddings, and then the different parameters and their sizes they also mention here. We won't go into too much detail into Gemma model, but all you can think about this is a decoder based model. So we have now vision encoder, we have a language encoder, which is a Gemma 2 billion model. And then finally we have a linear layer which projects SIGLIP output tokens to the same dimension as Gemma vocab tokens. So this vision encoder produced tokens whose dimensionality is different from this text tokenizer. So we need to project it to the same dimensions of vocab of text. Finally, this is how the inputs are passed to these models. So the image is passed through the SIGLIP image encoder and the linear projection layer, and it is converted to image tokens. Then we have beginning of sentence token. This is a special token. Then we have prefix tokens. These are the text tokens which are the input to the model. So you can see in this image, this prefix token will be these prefix tokens will be where is the photographer resting. This thing will be image tokens, this thing will be prefix tokens, and then the final output will be the suffix tokens. And then we have end of sentence and then some padding tokens to make it of equal length. Now coming back to this figure of how the attention works, or which tokens can tend to which is really important. So we have this image tokens, this special token, and this prefix tokens, and then we have the target of suffix tokens. So all of the input image tokens and prefix tokens can tend to each other in a bidirectional fashion. And the idea is that if image can, and this is different from causal attention where the token can only look at the tokens behind it. It cannot look at the tokens in front of it. Whereas here, the image token can really look at the tokens in front of it. For example, this input 2 token here, it can also look here or attend to this token. And the idea here is that if the image tokens can attend to the text tokens, it can really adjust its activation to match the task. For example, here we have the vision question answering task. Where is the photographer? You can imagine we can have another task. We can give it the same image and ask it to now detect the photographer in this image. Put text needs to output the coordinates of the bounding box. So the image encoder can also adjust itself by looking at the task ahead, what task is being asked. A bit more detailed, the images, they always resize to 224, 448 or 896 square images. They don't maintain the aspect ratio. So since the input size of images is fixed, this also leads to the fixed number of image tokens. For 224 we have 256 tokens and so on and so forth, which we place in front of the image tokens. So the image token is placed in front, then we have beginning of sentence token, then we have prefix token, the expression token we have, which is basically \n, then we have suffix tokens, end of sentence and padding tokens. So how did they train this model? They use this 3-stage or 4-stage training if we consider the stage 0 also. So stage 0 is unimodel pre-training. So each model is independently trained. The Vision SIGLIP model and the Gemma 2 model, both are trained independently before joining them together. So since they already have this, they have this SIGLIP checkpoints and they also have Gemma checkpoints, so they did not train it, they use the pre-trained model. The second stage, or stage 1 actually, because in stage 0 we did not do any training, we just use a pre-trained model. Stage 1 is the multi-model pre-training. And in this stage, they actually now connect these uni models, this language model and this vision model in this architecture, and now they train the models. And one important thing in this PaliGemma is that they don't freeze any part of this model. They train the entire network, including the vision encoder, linear projection layer, and the language. Most of the cases, some part of this model is generally frozen. For example, vision encoder is generally frozen. Mostly this transformer decoder is also, or this language model is also frozen. Add these adapter layers in between and we only train them normally. But in this case, they train the entire thing and they don't freeze anything. Since they train it on a wide variety of tasks, it gives model a wide range of information or knowledge. And then we can fine tune it to our particular task. The thing is that this vision encoder and this language decoder models are trained unimodally. They have not seen the tokens from each other. So initially when we connect the language decoder after this vision model, we'll get the gradients from this language decoder model, which can destroy the learning of image encoder because they are not aligned initially, right? So they have not seen each other tokens so far. So what they do is for vision encoder, they linearly ramp up the learning rate, right? So they start from 0 and linearly ramp up to the target learning rate. It does not quickly get the destructive signal from LLM and completely forgets what it has learned during unimodal training. Right, so we have this multimodal training. So for the stage 1 is trained on 224 cross 224 square images. And the resulting number of image tokens after it is passed through the vision encoder and the linear projection layer is 256, and the sequence length for text is 128, and they train for a total of 1 billion examples. Now for stage 2, it is the same as stage 1. The only thing they do is increase the resolution of images and also increase the text length. It is a common trick to make the training more efficient to first train on smaller images and then scale to much larger images. And tasks like OCR also benefit quite a bit with higher resolution. They also say that we increase the text size to 512 tokens. And finally, in stage 3, after doing all this pre-training, and we'll see what kind of pre-training task it sees, we have these 3 different checkpoints of trained at 224 resolution, 448 and 896. We can transfer it to downstream tasks. Some tasks can be COCO captions, visual question answering, video captioning, or even object detection and segmentation, right? And after we have this pre-trained, we then do this fine-tuning and pre-training task mixture. Now for stage 1 and 2, before the transfer, we do this pre-training. And what kind of different tasks we are talking about here? So we have this caption tasks. So we have image caption. We have OCR, like reading text from images. We have question answering, like questions are on these 35 different languages, but answers are in English. So what we do is, in the prefix of the text, we append these tasks that we want to do. The input tokens will be the image tokens, beginning of sentence, and then in the prefix tokens, if we want to do OCR, it will be like OCR here. If we have object detection, it will be like detect, and then the class name separated by commas. I think these are the standard vision language tasks, but the important is that they can also convert pure image task into this API or this framework. For example, they can have an image, then they, in the prefix they will have detect, and then the classes they want to detect separated by these semicolons. Similarly, they will have this segment, and we will fine tune this model on this object detection. So we'll go through the code and see how this is done. And similarly for segmentation, we can have a segment and then the different things, and so on for grounded captioning. Before we go to the code, let's look at some of the ablation studies. So the first one is new token initializations. What we want to do is add some special tokens for special tasks like segmentation and object detection. So original Gemma language model don't have those special tokens, but since we want to do this special task and we want to indicate the output of those tasks by special tokens, so we need to add it to the vocabulary. So for object detection, we add these 1024 tokens, and these location tokens determine the XY coordinates for object detection output. I will show the example so it will become more clear. And similarly for segmentation, for polygon representation, they added 128 from seg 000 to seg 128 special tokens. So they added to the vocabulary of the Gemma model. And then we also need to change the size of the input of the model and then the output of the model, since the input of the model has changed and also the output. So how do we initialize those? And this shows here that the random initialization basically works good. So they showed that they can use some special other methods, but using the small standard Gaussian initializations work the best. To freeze or not to freeze, as that's their main point, that they did not freeze the vision encoder or the language model, and they trained everything for stage 1 and 2, and they showed it that the performance is better than freezing them. Then the connector design, right? So we consider 2 connector design, a linear connector and an MLP, a hidden layer with a Cayley nonlinearity. And overall, they conclude that in our case, the linear connector seems preferable to MLP connector. So yeah, that's why they are also using a linear connector. Then image encoder with or without. One important thing is, do we really need an image encoder? Right? So can we directly take an image, break it down into tokens and append it here, or pass it through a linear projection layer and append it to the language tokens, and can we use the Gemma language model to decode those tokens? But in their experiment, they showed that this is needed. If we remove this vision encoder, then the performance gets really bad. And they want to show is the image resolution actually important, or the sequence length or the image tokens that it produces are more important. If we increase the image resolution, we can see more fine grain detail in the image and the task performance should improve. So that's the first one. Second one is also, since we increase the image resolution, the number of tokens, image tokens increase, and resulting number of flops increase, and so the capacity of the model increase. And they want to check, is the model performance better once we increase the resolution? Is it because we can see more fine grained detail, or is it because the length of visual tokens has increased and so flops and capacity of model has increased? So, and in their ablation study they showed that both contribute equally. So the first one is the 224 pixel image, how they perform. Now this orange bar is, this is 448 pixel image, but it is resized to 224 first. So if we have a 448 image, it is downscaled and then upscaled back to 448. So in this way it has lost all the detail which was in the original image, but still it is a high resolution image. So the number of tokens will be more and the capacity of the model will be more and the flops it needs are more. So it increased the performance of the model even though the detail in the image is the same as 224 cross 224 image, because it was resized first and then upscaled, but the number of tokens has increased. And it further increased if we use the native 448 cross 448 image. So they showed that both of these things contribute equally to the task where resolution is important. For example, OCR, object detection, segmentation. And the last ablation study I want to check is resolution specific checkpoints really important? So they released 224, 448, 896, three different checkpoints of three different resolutions of images. And they also showed here that it matters. So for example, if the original pre-training task was done at 448 and then you fine tune or transfer it to 224, then the performance decreases, which makes sense. And then they did some more ablation studies. For example, if you have a 448 cross image, you can divide it into 4 224 cross image, then the performance improves. The best performance we get if we have the pre-training done on 448 image and we fine tune it also on the same resolution images, right? So the best way is to maintain the native resolution and fine tune it also in the same resolution as it was pre-trained in. Okay, so now let's go to the code and now let's fine tune this model for object detection and see how it works. This is the PaliGemma simple repo that I created, and what it does is it takes the PaliGemma implementation of Hugging Face and fine tune it on object detection dataset and also visual question answering dataset. And I will go through the object detection part, and what you will see at the end of it is that we can take a PaliGemma mixed tune model. So mix means that it is trained on number of tasks like we discussed in the paper, including object detection and segmentation, and then we will fine tune it on our dataset. So I have this very simple cats and dogs dataset. It's a subset of Coco, but it only has 1000 images for training and around 100 images for validation and testing. So before fine-tuning, the model already performs quite good. So if you see on this, we want to detect cats and dogs, and that's what we do in the prefix or prompt. I will show you in the code. And the model does fairly well. So green box is a ground truth and blue box is the prediction. But after fine-tuning, it becomes much more aligned. This second example is more interesting here. If you can see, I will go a bit more into detail. So if you see, there are two dogs, and the ground truth says that there are two dogs. One is this and one is this big box in green, but the model prediction is just one dog because they are close to each other and including each other. So it's a hard problem. So it's generally a little bit harder example, but after fine tuning, the model can also identify the second dog. So this is a very simple example of fine-tuning cats and dogs. The model already performs quite well. But suppose if you are using any specific domain, or if you are in manufacturing, agriculture, or medical domain, your data will be highly specialized and the model will not perform quite good out of the box. So in that cases, fine-tuning really helps. And while doing the fine-tuning, we will also go through the architecture of the model. So this is the script that trains the object detection model, train OD. and it is a very simple loop. So you can load the data sets is in Hugging Face dataset, this cats and dogs small detection. Again, it has about 1,000 images for training and 100 images for testing. I will go first to the how the dataset is converted into the right format for model training, and then we will go through each step of the model, how it works and how it correlates with the paper. Right, so I will use this breakpoint similar to what I did in the last video to go through step by step here. So the first thing we do is we load the Google PaliGemma 3 billion mix model, which is trained on 224 cross 224 resolution images. We download this model here. Now we download the dataset. It will get the dataset from the Hugging Face, but I already have it in my cache, so it will just load it from there. Now we go through this training loop. This is a very standard training loop. If you go here, we create this dataset, training and validation. I will go through what happens in them. We create these loaders for train and validation. We create this model. We will be using LoRa for efficient fine tuning since I only have one GPU of 12 gigabytes. So the full fine tuning of this model is not possible on my GPU. I will be using LoRa to fine tune it, but I have disabled it at this point so we can go through the original model. And I will make a separate video on how this parameter efficient fine tuning works. And we create an optimizer which takes the model parameters. It's the main training loop. It's very simple. We first zero the gradient of optimizer, and then first we will go to the data loader, and this is how this data loader works. It takes the image, bounding boxes and labels. So for typical object detection you need an image, the bounding boxes that you want to detect, and what are the classes, for example cats or dogs, of those bounding boxes. So the main magic happens in this collate function, and what this collate function does is that it tells the data loader how to combine these different samples for batch processing. Right, so this data set can return separate items, but if we want to make utilization of entire GPU, we should combine this sample into one and then send it to our model. And this collate function tells the data loader how to combine these different items. So what we do, so for example here we are using batch size of 2. So we have 2 items and each item has image, boxes and labels which this data set is returning. It is returning these 3 things. And then we collect images in this, boxes in this and labels in this. Then we loop through, we can stop this breakpoint. Then we loop through these boxes, labels and sizes. We get the original size of these images. We will resize them to 224 cross 224 because that's what we are training the model for. We get all the unique categories here. So in this one, both of the examples has only dog. If there was dog and cat both in the same image, then it will be dog and cat. Then we define the prefix text, right? So if you go back to the paper, so we are trying to define this prefix text, which will become prefix tokens. And we discussed that this prefix token will represent the task that we want to do. In this case, we want to detect the objects in the image. So this will become detect, and then we will join all the categories, which is in this case it's just dog, but in our dataset can be dog and cat both. So if we go here, then the prefix tokens become detect and dog. If there was a cat also, it will become detect space cats space semicolon space and then dog. Next thing we do is loop through these boxes and categories and convert them into the required format that we require for object detection. And if you go back to the paper, what we need for object detection, we want to input the model prefix like this, detect space cat for our example, space colon space dog. This is what we are doing. And for what we want the output to be like is like this. So for detection, we have this format. We want to encode the coordinates from 0 to 1024, which are normalized coordinates. Right? So how to do that? It takes ymin, xmin, ymax, and xmax, and that's just the format how Gemma is already trained on. So we are also following the same format, because Gemma model trained on object detection output in ymin, xmin, ymax, xmax. Normally object detection output in xmin, ymin, and xmax, ymax. I'm not sure why they have chosen this format, but anyway we will also choose the same format, so the model don't have to learn the remapping of these coordinates. It does not waste the learning steps in these remappings. And what happens here is we take each coordinate, we divide it with the scale factor, which is our image size. Is we have rescaled the image to 224, so this coordinate will be also rescaled to 224, and then it will be scaled up by multiplying by 1024, and then just we take the min, so we are sure that we are inside the range, and we take it in this format. So it will be from 0000 till 0 till 1023. So this is how we encode the bounding boxes. We also add the image token in front of the prefix token, which also comes from this paper. So we add the image token, and then we have the prefix tokens, and then we have the suffix tokens, which is the output we are trying to predict. And the output we are trying to predict becomes like this. So these locations come from this function. We just normalize the bounding box, and then we upscale it to 1023, and we append the category name here, and now we pass it through the tokenizer. So we now have the text, which is like this. We have the image token detect dog, we have image token detect cat. These are the inputs, so these are the two. So we have two images, one has dog, one has cat. So the input prefix text becomes like this, and the output of those images should look like this. We have the locations or the coordinates of the bounding box and the category of the class for first image, and then for the second image also. We want to convert it to this format. What we have done so far is we have image token, we have prefix text, not tokens, we have created prefix text, we have suffix text. Now we want to convert it into this format. We should have image tokens followed by beginning of sequence, prefix tokens, separators, suffix tokens, end of sequence, and then pair to make it of equal length. Now let's go through the tokenizer, how this prefix text and suffix text will be converted to this format. So this is the tokenizer. First it does some checks that the input is in the right format, and then the main meat of this tokenizer happens. What it does is go through each text. So we have a batch size of 2, so first it will go to the first example, then the second one. And what we do here is we replace the image token, which is image in these brackets, by the number of image tokens that we expect for our image to produce. So since our input image size of 224 is fixed, so this image number of image tokens are also fixed to 256, like we discussed in the paper. So we replace the image token, which is the first token here, with 256 image tokens, right? So it goes through this. So this is what it looks like. So we have 256 of these image tokens, and then we have detect, and we have dog. So these are the other two. This is the prefix text, and these are the image tokens, right? Then what we want to do is add beginning of sequence token. So we find here the rightmost image token, and then we add the beginning of sequence token there, and this is what's happening here. And then we also add this /n, which is a separation token here. Now what has become is one image token has become 256 image tokens. We have beginning of sequence token added. We have prefix tokens. We also add the separation token denoted by /n. We haven't added the suffix tokens yet, or these tokens, but this will happen here. So if we go here, so this is how the final prefix tokens look like. So we have 256 image tokens, then we have beginning of sentence token, then we have detect, cat, and the separation token /n. So we have successfully done up till at this point. Then moving forward, now coming to the suffix. Suffix is what we want to output from the model. And currently the input is like this. We have two of them since we have a batch size of 2 again. What we want to do is add end of sequence token after each of them. Right, so this is what it will do here. So if you see here, what suffix will become is this coordinates of the bounding box, then the class name, and then end of sequence token. And now we also pre-process the images. So remember, the images so far has been PIL images. So these are just RGB images. We want to convert them to tensor and also normalize them. So this is what happens here. And then finally, we pass it to the actual tokenizer. So this input string becomes the main text to be tokenized. The text pair or the suffix tokens are the output that we want to predict becomes the suffix token here. So it's important to pass it like this, because then we can also pass in return token type IDs, and then we will know whether the return tokens belong to the input strings or the output string, or actually, to be more accurate, to be input tokens or output tokens. And then we can only calculate the loss on those output tokens. And this is exactly what happens here. So what happens here is, if the input token type ID is 0, which means it belongs to this input string, then we set the labels to -100. So if you remember again from the last video also we discussed, so if something is set to -100, so during cross entropy, its loss is ignored using PyTorch, right? So if I print also these inputs, all the image tokens, like 256 image tokens are -100, and also the part of detect cat or detect dog is -100 because they all belong to prefix token. And only the part which belongs to the output, which is the location of the bounding boxes and the class name, belongs to the suffix token. And for that we want to calculate the loss. Right, so the output of this tokenizer is, again, we have these input IDs, which is the prefix plus suffix both tokenized. We have token type IDs which indicate whether it belongs to the prefix token or the suffix token. We also have attention mask, which shows which part to attend it, because for this example we have exactly the same length of input tokens, so all of them are 1, but normally if you have some part which is padded, so you will see zeros here. And then finally we convert these tokens to BF16 and then move it to our device. So once we tokenize the input, so our batch become input IDs, token type IDs, attention mask, pixel values, and labels. We can pass it to our model, get the loss, do the backward pass, and update our model. So let's go through what happens in the model and how it relates again to the paper. So if I do the forward here, these are just some checks which are not really important. This is the important part. So the first one is we pass this pixel values, which is again tensorized images. So we have two images, both of 224 by 224 and RGB image. So this is the shape of the pixel values. It is 2, 3, 224 by 224, and we pass it to the get image features. Remember that the image feature, this is a Siglip trained image encoder. It can be any other vision encoder, it can be CNN based or transformer based, but like we discussed, SIGLIP based vision model performs quite well. Actually now even SIGLIP version 2 is out, maybe we can go through it also sometime, but this model works quite well for vision text tasks. Pass it to the SIGLIP vision encoder, and we get the last hidden state, and its shape is 2, 256 and 1152. The 256 is the number of tokens, vision tokens now, or image tokens. 2 is the batch size, and 1152 is the dimension of those tokens. And now we can project those tokens to match the dimension of text tokens. And this is exactly what this multimodal projector does. If I do the forward pass and I come here into multimodal projector, it is just a linear layer which goes from this 1152 image token dimension to 2048 text token dimensions. So we can concatenate our image tokens with the text and pass it to the Gemma model for decoding. If we go back to the paper, this is how it relates to. We have this SIGLIP image encoder. We pass it through the linear projection layer to convert it to the same hidden dimension as the text token, which is 2048. And then later we will concatenate it with the text token and pass through the Gemma model. So this is how we get the image features. Now the next thing we are doing is that we are taking the image token IDs in our input IDs. So remember, we have these 256 image tokens. Now when it is tokenized, it is given a unique ID, and for image token it is 257,152 tokens. So what we do is we create a mask where input tokens are equal to image tokens, and remember we have 256 again. And then what we do is we use this mask scatter. So this mask will be like true, 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 true until 256, and then false, false, false for the text where we have this detect cat or detect dog. For those it will be false. For all the image tokens it will be true. It will take that mask. It will take those image features, which remember now are projected to 2048. So their shape is 2, 256, 2048. And it will replace the input embeddings in those positions with the image embeddings. We have 256 positions here for each batch, and we similarly have 256 positions here, and we have the same dimension now. That's the purpose of using the linear layer, to project it to the same dimension so we can concatenate this with the text tokens. So once again, what this mask scatter does is where this special mask is true, where we have the image tokens, it replaces it with the actual image features which comes from here. So this is a design choice of doing attention. Another way we saw in last video in Flamingo, we could have left the image token as it is. We could have inserted these vision tokens in this layer as a separate variable, as a state, and then we could have attended to those rather than replacing these image tokens with these vision tokens. But it's just a design choice. I really liked how PaliGemma is doing it. It is more elegant rather than inserting the state of image tokens in those decoder layers or these adapter layers. This one seems much better. We just replace the image tokens with these image features. And then finally, I think the important thing is also how to create this causal mask. They mentioned they want to do attention like this. They want the prefix and image token to be bidirectional, like both can attend to each other, and the suffix token should be causal. It can only attend to tokens before it. It cannot attend to token like after it. So after this token it cannot attend, but once it is an output token 2, it can attend all to the previous. This thing is done by this function update causal mask. So far our attention mask consists of just ones, which indicates which values are really buried. In our example, both sentences were exactly of equal length, so nothing was padded, otherwise we should have seen some zeros here at the end. So what this function does, if I go here, and this is the main crux of it. So I have created a notebook to make it more clear what this does in this playground, right? So first we just import this torch. Min value is float minus infinity. It can be a very small number of that data type. And then what we do is create the mask of length sequence by sequence length, or here it is target length, but for us both are the same. And then we got this causal mask. You can consider these rows of dimension sequence length and also these columns of dimension of sequence length. So initially we have like minus infinity everywhere or very large negative number. So why we have this is like exponentiated in the softmax, it will become 0. So right now we are not attending to anything, and whatever will be 0 will become 1. So exponent of 0 become 1, exponent of minus infinity becomes 0. So the first thing we do is create upper triangular matrix, right, like this. And what this function will do, it takes a causal mask and create the upper triangular matrix above the diagonal one. So it will create all the zeros here, and whatever the values were already in the matrix will upper right part. So this is actually a causal mask. So how this is causal, this is sequence length by sequence length. The first token can only attend to itself, so this is 0. Whatever is minus infinity it cannot attend to, because when exponentiated in softmax it will become 0 and this will become 1. The second token can tend to the first token and itself. The third token can attend to itself and the previous tokens. So it cannot attend to any token after it. It can only attend to token before it and itself, of course. And so on and so forth. Like the last can attend to everything before it. Now if we create also the token type IDs, and remember token type IDs represent whether the tokens belong to the prefix or whether it belong to suffix. And this is where this token type IDs is used for, because what we want to do is for prefix token we want to create this bidirectional attention, and for suffix token we want to create just causal attention. And for prefix this token type IDs will be 0 and for suffix it will be 1. So what I'm doing here, I'm just taking an example, like initially all are prefix and then I converted the last two elements to suffix, and this is how the final mask should look like. So from the causal mask you take up till mask length and you fill this mask to where the token IDs are 0, and this none is basically just to match the dimensions, just to create an extra dimension to match of causal mask. Wherever the token types are 0, make it equal to 0. The first three token type IDs are prefix token. This will only affect the prefix tokens, which are the first three token type IDs. So wherever these infinities are, these and this, it will also become 0. It will not affect the suffix token. So what happens if we go to the original attention paper, we have these query keys values, we multiply them according to this query key transpose, scale it, multiply with the mask, or in our case we are using torch scale dot product attention, and in their documentation they say if the mask is boolean then it will indicate which should be part of our output, but for our case the mask is float, a float mask of the same type as query and key that is added to the attention score. So what happens is that we multiply queries keys and then add these values, so wherever minus infinity is added, so all the values at those position will become minus infinity, and then if we'll do this dot softmax, so wherever it was minus infinity it will become 0, because if you exponentiate it, it will become 0. So right, going back to our code, this is exactly what is done here. They create the causal mask, they create this upper triangular matrix for this causal mask. Wherever there is padding token, they also do this min d type, replace it with min d type. But for R, if in this example there is no padding token, so this will just stay the same. And here they are doing exactly the same. Wherever the token type IDs are 0, it will allow the bidirectional attention. Okay, so this is how the mask is created, and I think that's actually the main 3 things in this paper. How the input is handled, how the image tokens are handled, and how this block attention is handled. We pass it now through this language model, which is a Gemma decoder based language model. It's not too interesting. I won't go through too much detail into this, otherwise it will become too big, but I can create a separate video what it does. But the important thing is how these causal masks were calculated, how these tokens were calculated, how this input embeddings is calculated, and how the image embeddings were inserted into these text embeddings. Once everything is in text tokenized form, we can pass it through this Gemma model or actually any language model, and we get the outputs. And the output logits we get has a shape of this. We have 266 is the sequence length, where 256 are just the image tokens and the rest of the tokens are prefix tokens and the outputs tokens. So all combined is 266. And 257,216 is the size of vocabulary of this model, including special tokens, including image tokens and everything. Now going to the loss. So if you remember, for autoregressive language model, what we do is for each token we are trying to predict the next token. So the logits become all logits except the last one, since we don't have the next value for the last one, so that becomes the logits. So the labels become from second token because it's a 0 index, so the first is actually the second token till the last. So remember, where the labels are -100, we saw in the pre-processing, wherever we have the prefix tokens, so we don't calculate really the loss during those prefix tokens. We only calculate the loss in these output tokens. And yeah, the loss is just cross entropy, and we pass the loss through here, and the output is just logits plus loss. Right, so if we go here, this is the output from the model, which is loss and logits and pass values and hidden state. We do the backward pass. Now if I do the backward pass right now, it will throw an error out of memory, so you can see, and it throws an error because this model is too big to be trained on my single GPU, which is only 12 gig. So what we need to do is parameter efficient fine tuning, and specifically LoRa. It's quite simple, so you can define a LoRa config, and whatever models you had, you wrap it in getPEF model and you pass it your original model, and that's it. You get the LoRa model here. And in the target modules, this specify which modules you want to add the LoRa layers to. So I will actually cover it in a separate video, but very basically what it does, it converts a high dimensional matrix, for example 512 by 512, to 512 cross 16 and 16 cross 512. So it converts a very big matrix into 2 smaller matrices. And in this way, you can only calculate the gradients and update those LoRa layers instead of the entire model. So if you want to do the training, you can just run this train OD for object detection, and you can of course replace this dummy dataset with your dataset. OD, you just do Python train OD, and yeah, we'll start the training. Now training is happening. First actually it is validating, just generating what the original model results look like, then it will train, and then you will see the results which I already showed before. Okay, so one thing I want to show how the text is decoded. So for example, the output of this model can be like this. It's like location 505 whatever, these are the coordinates of bounding boxes, and then the class name separated by semicolon, and then again the location and then the class name. So one way of doing this is using regex. So this is the regex pattern I'm using, and you can test it in this playground. And you can also test it if this is the regex pattern and this is the input, it will extract these coordinates 0505, 875, 543, 905. These are the normalized bounding box coordinates, and same goes for here, and it extracts the class names, right? So using this pattern, you run it on the output tokens and you extract the coordinates. We assume that we only detect the 4 groups, and the first 4 groups belong to the coordinates, and then we extract the last one belong to the class. Then we unnormalize the coordinates to the image coordinates, and then we just draw. The thing I want to show is like PaliGemma 2 mix model is also released. So what we have covered is PaliGemma 1 or just PaliGemma. The next one on this series is PaliGemma 2, which is exactly like PaliGemma, except they replace the Gemma decoder model with the Gemma 2, and it is trained on much more data, so it is a bit more accurate. But they also released it similar to PaliGemma into these 3 resolutions: 224, 448, and 896. If you look at this PaliGemma 2 model, it is exactly the same again, trained on higher number of tokens and tasks, and they replaced the language decoder to Gemma 2. And they just released a few days back the PaliGemma 2 mixed checkpoints, and you can also see I was just testing it and it performs quite good in this data set, this PaliGemma 2 model. But again, this is a very easy data set. That's it. I will see you in the next video.